ionic bond is basically electrostatic attraction between oppositely charged ions which are in a crystal lattice. Okay, there's some extra stuff here, just ignore that. So three main points there. It is a strong electrostatic attraction. So that's the kind of force that you have. The force here is electrostatic. Okay, what is it between? The oppositely charged ions. That means there's ions. Ions are atoms or group of atoms that have charge on them. They're not neutral. Okay, and they're in a crystal lattice. So three words, I'll repeat again. The strong electrostatic attraction, the force that's there between oppositely charged ions, the particles that are there in a lattice, the structure that it has. Remember, no matter what kind of bonding you have, you are going to talk about these three things: force, particles, structure. So the forces here are electrostatic. The particles here are cations and anions. Cations have positive charge and anions have negative charge. And thirdly, the structure is crystal lattice. It is a regular arrangement in which these particles are arranged. And this is what ionic bonding is. Okay. Now, to understand how ions come about, we have to understand the dot and cross diagram. Every dot and cross diagram simply tells us that you have atoms, and these atoms have electrons, and those electrons are either gained or lost. If you want to go through that, how is electron gained or lost, just remember that depending on where it is in the periodic table, anything has a certain number of outer electrons. So group 1 will have 1 outer electron, group 2 will have 2 outer electrons, group 7 will have 7 outer electrons. There are a few atoms for which we do not know the outer electron right away, which we call transition metals. And for that, you just have to remember how many it loses. Now, the two main numbers for atoms are 0 and 8, as I taught yesterday. So things that are in group 1 or 2 or 3 will favor 0. So they lose that. And that is the number of charge that they have. Similarly, non-metals, they favor 8, which means that they will simply lose gain electrons and they will make a negative charge. Yeah, so over here we have some examples: sodium chloride, magnesium oxide, calcium chloride. Okay, so if you look at it, sodium chloride over here, it has lost 1 electron. Sodium has 1 electron in the last shell, but in this case, it has lost that 1 electron and become positive ion. Similarly, chlorine has 7 in the last shell. But do you notice this cross at the top of this last shell, this one? This is telling me that an electron of sodium has transferred to chlorine. Similarly, over here we have magnesium. I've drawn it in a different way to show that you can also draw it like this, that magnesium had 2 in the last shell and they were both taken away. And you can see that they're both present here in oxygen. Okay, and these are the ones that have been transferred. Similarly, calcium chloride over here, what's happening? Calcium is in group 2, so it will lose 2 electrons. But chlorine, which is in group 7, needs just 1 electron to convert to an ion. So what does it do? 2 chlorides are formed, each with 1 electron taken from calcium, and they will form these ions. Okay, so these three I'm giving because these are very important when it comes to illustrating different exam questions. They usually refer to these three in the exams. Now, usually the dot and cross diagram that they ask you, they mention what level of electrons shells you need to show. If they say in the exam that only show the last shell, show the last shell. If they do not specify, show all the shells, just to be safe. Okay, and use different symbols. Dots for one atom, crosses for the other. Doesn't matter which one you put dot and which one you put cross. Okay, so that's the thing. All right, so we have calcium chloride, which means that calcium has lost 2 electrons, but chlorine has gained only 1 electron. Each chlorine has gained 1 electron. You do not need to make 2 chloride ions. Now, another important thing, you see these square brackets around them? Whenever you draw dot and cross diagram for ions, make sure you put that there. So here are some questions that I want you to answer. First, if they give you in the exam, define ionic bonding, what should be your answer? It should be that ionic bonding is a strong electrostatic force between oppositely charged ions in a lattice, in a crystal lattice. So you see, you have talked about forces, you have talked about particles, you have talked about structure. You can also write the history of that thing. Like you can say that ionic bonding is the bond formed by a transfer of electron. That's also fine. You can do that if you. Okay, second one. How is an ionic bond formed between atoms of calcium and fluorine? Now, this is also related to the exam. And when they say explain, you have to talk about how many electrons are gained or lost. But not just that, you have to specify which atom has lost and which atom has gained electrons. So for example, in this case, we'll say that calcium loses 2 electrons and fluorine gains 1 electron each. So you get 2 marks. 1 mark for specifying how many electrons are gained or lost, and second mark for specifying which atoms gained, which atoms lost. And obviously, the third part is about drawing the calcium ion and fluoride ion. So I'm hoping that you'll be able to draw them. How do you draw them? Draw the atom. For metal, remove the last 2 electrons. For non-metals, make 8 in the last shell. Okay. And once you have that, put square brackets around them and the charge, and you have your dot and cross diagram. You don't need to draw 2 fluorides. Just one would be enough. Pick any one of them and draw it. Then send me that picture in WhatsApp so I know whether you've done it correctly or not. Okay, I've received one answer. The rest of you, please make sure that you do it by today. So just pick whatever compound you want to talk about and take its ions, draw it. For metals, you have to make it 0 in the last one, and for non-metals, you have to make it 8 in the last one. So it's really simple. And then you put square brackets around them. Always put the symbol in the center. Some students have a tendency that they write the name at the bottom of the diagram or somebody. Just put name in the center so that you know which atom you're talking about, and not name the symbol, I mean. Okay. So that's important. So ionic compounds are the ones that are formed from ionic bonding. Now remember one thing. The formula for any ionic compound simply tells us the simplest ratio in which they're combined. Because you see, we have a lattice in which we have thousands upon thousands of these ions. So they don't have what you say a fixed number of ions in every compound. Every crystal may have anywhere between 1 billion to God knows 50 billion ions. So that is why we don't write the numbers there. For example, in sodium chloride, we'll say NaCl, because that tells me that for every 1 sodium ion, there's 1 chloride ion. Similarly, if you have CaF2, that means for every 1 calcium ion, I have 2 fluoride ions. So it's the ratio that we write in the formula. Okay. So there's an infinite assembly of ions arranged in a lattice, and that's how we know them. Now, this attraction is really, really strong. And because there's so many of them, they are crystalline solids. Crystalline means they have crystals, and they're solid because they have high melting point. Why do they have high melting point? Because they have strong electrostatic force. Remember, melting point, boiling point, volatility, which means how easily something evaporates, density, all of these things relate to physical properties, and most physical properties depend on force in them. So over here, ionic compounds, they all have very strong electrostatic force. Because of that, they will have high melting point, high boiling point. Their lattice will require high energy to break. So when you have something like this, always talk about energy as well. So for example, if they say, why does a certain ionic compound like magnesium oxide have strong high melting point? So it'll say that there are strong electrostatic forces in the ions, which need high energy to be broken, which is why it has high melting point. Now, same idea goes when you're comparing ionic compounds. Like if you have one ionic compound and you're comparing with another ionic compound, you'll simply have to see, okay, sodium chloride has a lower melting point than magnesium oxide. Why is that? Melting point depends on energy. Energy requirement depends on the force. So you'll say, okay, the forces in sodium chloride are weaker than the forces in magnesium oxide. A better answer would be you specify the forces. Even better, you specify the ions that have the forces. So electrostatic forces in sodium chloride ions are weaker than electrostatic forces between magnesium and oxide ions. So the energy required to break those forces is less, which means melting point of sodium chloride is less. So see, we have talked about the two requirements. All right. Now, whether they conduct electricity or not depends on whether they have free charged particles or not. Because you see, electricity is flow of charge. So if you have charges that can flow, that can move, electricity will be conducted. Now we have a lattice. That lattice is strong. That means most ionic compounds, in fact, all ionic compounds will not be able to conduct electricity as solid, because even though they have charged particles, they are not free to move around. So they will not conduct electricity. But once you put them in water, or once you make them like melt them, then they have free ions, so they will conduct electricity. Okay, so what's the reason that they conduct electricity? As liquids, they have free ions, so they are able to carry charge. As solid, they don't have any free ions, so they will not conduct electricity. Remember, never to write electrons for ionic compounds, because electrons are not free no matter what. They just transfer from one atom to another atom. They're inside the atom. They're not free to move. It's the whole atom or the whole ion that moves if they have to conduct electricity. Ionic compounds are mostly soluble in water, but we don't talk about solubility in O-level. So here's an example of sodium chloride lattice. You can see that sodium is shown in yellow and chloride is shown in green. Can anybody tell me why I chose yellow for sodium and green for chlorine? It is because sodium metal is yellow and chlorine gas is green. But once they come into this lattice, their colors go away, because color is a chemical property. Sodium is yellow because of the arrangement of electrons in there, and chlorine is yellow because of the arrangement of chlorine is green because of the arrangement of electrons in there. But once you form lattice, these colors go away because now their arrangements are different. And that is why sodium chloride is white. So it doesn't have any color. More than that, this is a fact that to have colored salts, you need transition metal ions in there. We don't have any transition metals, so it will not be green. So this is just an illustration. Okay, so you can see that the ratio of sodium ion to chloride ion is 1:1. Over here, we have one sodium ion. It is surrounded by 6 chloride ions. Remember this. Sorry, that's my dog. Yeah, so we have 6 chloride ions. Okay. Similarly, over here, we have a chloride ion, which is surrounded by 6 sodium ions. Now, we don't write Na6 and Cl6. We basically write the ratio in which they are. So sodium chloride means for every sodium ion, there is one chloride ion. Compare this. Now, another important idea is that ionic compounds are hard. So the reason they're hard is because they have strong forces that don't allow them to bend, or don't allow the lattice to be bent. Uh, Whether they break or not, that's not in your syllabus, so we'll skip this one. This for IGCSE, but I don't see any student from IGCSE in the class. Okay, so for this question, it says which lining of electrical furnaces, we need something that will withstand high temperature, and we need something that does not conduct electricity, because we want it to be lining the furnace. We don't want it to use the electricity that we have. So strong forces are there, which will give it a high melting point. So that's one. Yes. Ionic bonding, yes, because it will not conduct electricity as solid. And electrical conductor, of course, it's not a conductor. Okay, so the answer is A. Now, as for the part of why ionic lattices, just for IGCSE, remember that ionic lattices are hard. They do not bend easily. But more than that, if you apply force on them, they break. Okay. So the layers which are there for ionic compounds, they just break right away. They don't bend, they just break. So that's another idea for IGCSE that you need to remember, that they're brittle. For O levels, just knowing hard is enough. But for IGCSE, you have to add that they're brittle. Okay. So that's ionic compound, ionic bonding. Any questions in those? So the main ideas were, what is ionic bond? So we had to talk about it is the strong electrostatic force between oppositely charged ions in a crystal lattice. Okay. And then the second main point was, how do you show ionic compounds? So you use dot and cross diagrams to show those ions. And for that, you just draw the atom as you would. And for metals, you make the last shell 0. And for non-metals, you'll make the last shell 8. Use different symbols for different atoms. And then you put square brackets around them to show the charge. Third, properties of ionic compounds. Ionic compounds will not conduct electricity. They will be hard. They will be brittle. They will have high melting and boiling points. And that all of it comes from the fact that they have strong forces. And those strong forces in solid keep the particle together. They're not free to move, so they don't conduct electricity. In liquid, the particles are free to move. The lattice breaks down. They conduct electricity. They're hard because, again, the forces don't allow them to move as much. They break if force is applied. And to overcome these forces, you have to supply a lot of energy, which is why they have high melting and boiling. So the MCQ required us to know what property of magnesium oxide helps to explain why it is used in lining electrical furnaces. So remember, we have a furnace. It will have high temperature. So we're looking for something that has a high melting point. So that is a yes for strong forces because we want it to not be melting at high temperature. Secondly, we don't want it to conduct electricity. It is the lining, it's the outside wall of a furnace. We don't want it to conduct electricity. That's why it is not a conductor. And why is it not a conductor? Because solids are bad conductors when it comes to ionic compounds. Now, another important question from the exam point of view is when they compare two things. So whenever they're comparing, you have to compare the charge on the ions and consequently the forces that they have. So higher charges will have stronger forces, which means ionic bonding is stronger, higher melting point. They will conduct better when they melt. So all those things come into play over there. All right, so metallic bonding. It is different from ionic bonding in the sense that it has negative electrons where ionic bonding has negative ions, and it has cations, but they are also arranged in a lattice. So there's a similarity that it has cations and they're arranged in a lattice, and there's a difference that it has negative ions, but they're spread around all over. This thing is called electron cloud. It can also be called sea of electrons. It can also be called delocalized electrons. What happens? Metals, when they have last shell and there's no other atom to gain those last shell electrons, they just dump them out. They'll throw them away, offload them. So sodium has one electron in the last shell, and even if there's no other element to take it, sodium will simply throw it away, and that electron will be mobile. And because it is mobile, it will move around. Now, that will create a very strong attraction between these delocalized electrons and layers of positive ions. And that is why we call it metallic bond. It's a strong attraction between positive ions in a lattice and delocalized electrons. So what have we talked about? We have mentioned the forces. The forces are electrostatic force. The particles are positive ion and free electrons. And the structure is lattice again. Okay. So these sea of electron, these electron cloud, they're all free to move around. Now, here's how you'll draw them in the exam. This diagram is not ideal for the exam point of view. What you should do is that you will draw 3 layers of cations, which have positive charges on them. But they'll be, instead of showing these gray area that I used to show electrons, just use negative charges to show different electrons. And here's what you have to do. You have to mention electrons between the layers somewhere. Okay, don't just put them on the outside. Put them inside, scatter them around to show that they're free to move. And those electrons are randomly arranged. There's no fixed arrangement because they're obviously moving all the time. What is metallic bonding? It's the electrostatic force of attraction between free electrons or delocalized electrons or a electron cloud or a sea of electrons. All those would work with cations arranged in a lattice, and that gives metals their certain properties. For example, over here you can see these lattices. Sodium lattice has these randomly, so the dots are supposed to be freely moving electrons. Magnesium has double the charge, so double the electrons. Aluminium has triple the charge, triple the electrons. So electrons are moving around. So just draw at least 3 layers that are regularly arranged for cations and electrons are moving around between the layers. Okay. Now, obviously, how strong a bond is depends on how many electrons it has to contribute. So sodium is giving 1 electron, magnesium is giving 2 electrons. So the attraction in magnesium is going to be much stronger, which is why magnesium has higher melting point. The attraction is stronger. Similarly, aluminium has even a higher melting point because it has 3 electrons. Now, second question that they ask is when they ask you to compare which of these will be a better conductor. Now, aluminium will be much better conductor than magnesium, which is be much better conductor than sodium. Why? Because aluminium has 3 electrons that can contribute to the free cloud or freely moving electrons or the sea of electrons. So aluminium has that. So aluminium will be a much better conductor than magnesium because magnesium is given just 2 electrons and sodium is given just 1 electron. So you see, again, if you know the definition, you're able to tell all the properties. The definition was it is the electrostatic force between positive ions in a lattice with freely moving electrons. So you see, more electrons, more attraction. The lattice is there. So that means that the structure, we can talk about it. So metallic bonding has this structure. There are cations. So if you apply force on them, these cations will simply move to a side. And that's why we say that these are ductile and malleable because they have layers that can slide over each other if a force is applied without breaking that thing. Okay. So there is a strong attraction between sea of electron and the metal ions. So that allows them to not break. But more than that, because there are layers, these layers will simply slide over each other if you have more, if you apply a force, and that way they're ductile and malleable. Amal, which concept do you want me to explain? The idea of why some metals are stronger than the other, you're not supposed to give a reasoning for that. But why are some metals? The reason is simply that some metals give more electrons to the sea of electron than other metals. Now, if they've given more electrons, the charges will be higher and the forces will be higher. And because of that, it will be more difficult to melt it. It will be more difficult to break it. And it will conduct electricity better because there are more electrons. Okay. So it depends on how many electrons it gives. And that will determine its hardness, its malleability, its strength, its melting point, and its conductivity. Okay. So that is where the metallic bond comes from and the strength of metallic bond. Does that answer your question? Okay. So that is it. Metallic bonding. That's all about it. We have freely moving electrons. Those electrons simply go around and you can use them to conduct electricity. You have layers which slide over each other, making them ductile, malleable, strong. So you can make wires from them, you can make sheets from them. And that is all because these layers can slide over each other. So you see, it's really simple. You just have to know the definition really good and you know the key terms there. So for metallic bonding, what were the key terms? There is a layers of cations or lattice of cations with freely moving electrons, which we also call sea of electrons or electron cloud. And the attraction is electrostatic between these electrons and cations. So if I were to define metallic bonding, what will I say? It is the electrostatic attraction between freely moving electrons and lattice of cations. So I've talked about the forces, I've talked about the structure, I've talked about the particles. All right, next, its properties. There are layers, so that means it is ductile and malleable. These layers can slide over each other without breaking. It is soft because these layers can slide over each other without. It is strong because there are strong forces keeping them together, don't allow it to break. It is a good conductor because there are free electrons moving around, carrying those charges in solid. So there was an MCQ in the exam where they said which compound or which substance conducts electricity without breaking down. And the options were sodium chloride or water and all that. You see, metals don't break down when they conduct electricity, but every other compound, when it conducts electricity, for example, ionic compounds, and we'll see how they do that when we study electrolysis. When ionic compounds conduct electricity, they break down, but metals don't have to worry about that, because these electrons are, again, there's a layer, the electrons are moving around without breaking anything away. Okay, so that is what metallic bonding and ionic bonding is. That's it for today.